My name is Rob Evans. I'm from Jisc. We look after the Janet network, which is, I'll talk about in a second. I'm going to talk about how we've recently deployed some 400 gig single wavelength stuff on our network. So what Thomas was talking about was transceivers that go in your routers, switches. I'm kind of going to talk about the other side, the WDM side, the line side. So first of all, quick introduction. Some of you may know what Janet is, some of you may not. We're the national network in the UK for research and education. We connect the higher education sites, further education sites. And one of our focuses is enabling high-speed data transfer. So we have high-speed connections to Géant, which connects all the European equivalents to Janet, and which then connects on to other global endpoints such as Internet 2 and ESNet in the US. So we do a lot of everyday use. I mean, when the students are sitting there on their laptops looking at cat videos, they're using our network. Equally, when researchers are downloading terabytes of data from the Large Hadron Collider in CERN, they're using our network. We have quite a few large bioinformatics sites that exchange a lot of genome data. And to answer Fergus's question, everyone asks, so what's the difference between Jisc and Janet? Jisc is the company, Janet is the network. Neither of these are acronyms anymore, so don't ask me what Jisc stands for, or don't ask me what Janet stands for. Now, the network itself. So we have a whole bunch of, I think it's about 9,000 kilometers at the moment, of leased fiber from SSE Telecoms. On top of that, we have the Sienna 6500-based transmission equipment, which we manage in-house. Our routers are mainly Junipers, MX series, MX2010, MX960, and they provide the IP service, point-to-point services, peering edge, customer edge, DDoS mitigation. The current network has been in service. If you're aware of our history, you're aware that we've had Janet, Super Janet 2, Super Janet 3. The days where we were funded to kind of just rip out the whole network and replace it every 5 or 7 years are probably gone now. The current network was put in place in about 2013. The fiber contract is going to run until 2028. I mean, we're going to start doing a lot more of kind of just running as you run your networks, incremental upgrades as time goes on, rather than kind of rip it all out and start again. As well as the backbone, which we've always managed, there used to be a whole bunch of regional aggregation networks then. A lot of those were managed by local universities. So, for example, in Northern Ireland, QUB managed what we call NIRAN, the Northern Ireland Regional Aggregation Network. But now we've kind of brought all of those in-house, and we're in the process of rolling out a new architecture to all of those, in fact, based on layer 2 equipment, to get away from having 18 different architectures in our regions, a single architecture that our engineers can keep in their heads rather than having to look it up because everyone is different. There are slight differences for Wales and Kent because they have networks that cover all the public sectors, so health, doctor surgery, fire, police, and education. But apart from that, we manage it all. So, this is where we started at a year or so ago. This is kind of the standard diagram of the Janet backbone. The orange lines in the south are 4 by 100 gig. The green lines are 2 by 100 gig, and the black line is just 100 gig. So these are our main backbone pops from Scotland. As you can see, as with most networks, there's quite a lot of concentration of pops in London, because, as we all know, that's where all the traffic comes in. And most of the predominant traffic flow for us is from London and the southeast through to the rest of the network. So that's why it tends to thin out as it gets further north, is because we've dropped off a lot of traffic on the way. But where did we want to get to? So the idea is that as part of general keeping up with capacity, we wanted to upgrade the links that were 400 gig to 600 gig, the links that were 200 gig to 400 gig. Scotland, we were still okay with just 100. Sorry about that, Fergus. But that was the plan. And how did we go about it? So why do you want to do 400 gig? Our peak incoming traffic earlier this year, it was somewhere in the region of about 600 gig a second combined, mid-afternoon. Our traffic profile is slightly different to most residential ISPs. Our peak's at about 2 p.m. rather than late evening when everyone's watching Netflix. We have very low traffic about 6 a.m. It ramps up to until about 2 p.m. Goes down about 6 p.m. with about half of our peak traffic, and it plateaus to about midnight, then drops off again till about 6 a.m. We have an 88-channel Sienna system. We wanted to use some of the spectrum more efficiently. We were getting up to using about half the channels, or more than half the channels, in some parts of the network. And this network does need to last us for maybe another decade or so. Whether we'll be using the same transmission kits doesn't matter. But we wanted to try and use the spectrum more efficiently. Plus, we also wanted to save on chassis space. The card we were looking at for 400 gig does it on a single slot, whereas the original 100 gig line cards were 2 slots wide. You have the client side and the line side in 2 separate slots. So 400 gig is 8 slots. The chassis we're using are 14-slot chassis. So we're placing 8 slots with 1 slot, which the cost of space and power in data centers. It helps us expand. Now, I don't know who knows much about WDM kits, what a WSS is in a ROADM. A couple of people. So the WSS is the magic part of a WDM system. It's literally, well, not literally, but almost literally smoke and mirrors. You have a whole bunch of diffraction gratings, or more modernly, you use liquid crystal, and you tune it so that you have 88 channels, and it kind of bounces them off in different directions. So you can redirect. It's a wavelength router. You can redirect the wavelengths. Different wavelengths coming in on one fiber can be split out and go to different directions outbound. What we had was a fixed grid 9-to-1 WSS. Fixed grid means that it bounced those channels about in 50 gigahertz increments. And that wouldn't work for 400 gig. So where are we going to do 400 gig? Now, you might have thought that where we're going up to 600 gig would be a good place to do it. It's the busiest part of the network. We'd obviously get the best savings there. But changing these WSSs is a very disruptive process. All the traffic going through a node goes through the WSSs. They are wired. I'll show a little bit later some of the wiring diagrams. They have an awful lot of fibers going in and out of them, and they're basically connected in a mesh. So doing it in the busiest parts of the network is going to be quite disruptive. And some routes were slow down. Right? Some routes were a little bit too long to use the single slot 400 gig card, because it has a kind of a limited DSP ability. It's not the best card. It was the most economic one that we could use. So we decided to use the northern part of the network as the test. So going up from Birmingham to Manchester, across to Leeds, and down to Nottingham again. There, we required 400 gig of capacity between the nodes. So we could just replace the existing 100 gig cards with the 400 gig cards, then move those 100 gig cards down to the south to add the capacity there. Now, will it work? The 100 gig transmission uses DP QPSK. So this is 2 polarizations of light with quadrature phase shift keying. And it works or it doesn't. There's a lot of DSP. It's one of the reasons I was asking to answer DSP. There's a lot of DSP involved. If you look at how these work, there's really lovely kind of constellation diagrams where it shows what state the light's coming in, whether it's a 1, 0 or a 0, 1 or any of those. And before you kick in with the DSP and the forward error correction, what you have is kind of just this mess of dots on the diagram. Then the FEC kicks in, and it kind of really coalesces. There's a lot of maths involved in understanding what these bits of light coming into the transceivers mean. So the chipset that we use, the chipsets are getting ever more complicated, and what they have the ability to do now is they look at the signal-to-noise ratio on the line, and they can adjust the encoding accordingly. So the better signal-to-noise ratio you have, the more capacity you have. It uses kind of proprietary modulation formats based on QPSK still and various levels of QAM. But to know how it was going to work, we had to get an idea of what the fiber was. So the original fiber handover was now 6 years old. During that time, there'd been JCBs, there'd been all sorts of things that changed the fibers. So we needed to take them out of service and re-measure them so we can feed it into the simulation. Now, OSNR, the signal-to-noise ratio here is key. The existing transmission kit we had EDFA-based amplifiers. To get the OSNR better, one of the things that you can do is you can change to using Raman amplifiers. The thing is, Raman amplifiers actually do their amplification using scattering, but it shoots another laser the other way up the fiber, and the amplification actually happens in the kind of the 20 kilometers of fiber approaching the transmission kit. Now that means to get the amplification working, you need to have very strict loss requirements in that first 20 kilometers of fiber. And the Raman amps that we were using, they actually have an OTDR, a kind of a fiber tester that sends pulses down the fiber to check for losses within them. And if the fiber doesn't meet the specs, then it doesn't even turn on the amplifier. It doesn't even turn on the amplifier. It says, right, this isn't going to work. Go back, do some splicing. So we modeled the spans we had. We were good to go on the north-south links between Birmingham to Manchester, Nottingham to Leeds. But between Manchester and Leeds, Manchester to Leeds was about 0.42 dB out of spec. Leeds to Manchester, 0.09 dB out of spec. Now, Sienna have this thing that says, well, anything less than 0.3 is fine. So that still left Manchester to Leeds as 0.12 dB out of spec. And they said, well, okay, what will happen in that case is that the thing will ramp itself down to 300 gig. Okay, no big deal. We can cope with that. We'll have to buy another 100 gig to run separately. Now, how does the fiber get from the road to the rack without any splices that are going to affect the Raman amps? Now, the middle box, I didn't draw this diagram. Those of you that have been to Equinix MA1 might be wondering how we appear to have a patch somewhere on the top of an aerial, because I don't believe it's got 4 floors. But it goes, we've got the fiber that comes in off the road, it goes through to the supplier SSE's rack, it then goes through to an Equinix rack, it then comes through to another Equinix rack, it then comes through to our patching rack, and then it ends up in the transmission kit. Each of those has got a patch panel going back to back. And for the Raman amps to work, none of these losses must be greater than 0.1 of a dB. Now we've all seen what patch panels are like. That's never going to happen. So we went, we gave it an attempt to it. Went in, polished the connectors, cleaned them, put them back in, tried it again. In the end, it wasn't going to work, so we just spliced the thing. So we kind of had to miss out a lot of those patch panels and just splice it for the amplification to work. Now, going back to those WSSs. So the existing WSSs we had, they were 50 gigahertz fixed grid and have wavelength specific add and drop on the client ports. The 400 gig uses 56 gigabaud, the bit rate, in 75 gigahertz of optical spectrum. Now, 75 gigahertz of optical spectrum doesn't fit in a 50 gigahertz grid. So we had to change all the WSSs from the fixed grid ones to the liquid crystal flex grid, as they're called, and then add colorless add drop as well. Because instead of having the 50 gigahertz client filters, we now need to be able to add and drop 75 gigahertz signals. Just a simple matter. So remember I said there's a lot of cabling in these. This is the Manchester node, I think. Each of those lines is a physical fiber on the front of the Sienna chassis. So as I said, they're connected basically in a mesh. So there's 9 WSSs there, and each of them is connected to each other, as well as then to their respective direction onto the network. And we had to replace those. Well, we were doing this as a test, so we didn't have to replace all of them. We only had to replace the ones where the 400 gig signals would be going. So the orange ones there, the ones that go down towards Cheddleton and then down towards Birmingham, and the ones that goes to Southport and then onwards to Leeds. But the other thing is you have to do the colorless add drop as well. Now, these are 9-to-1 WSSs. We have 9 directions there. There's nothing spare to be adding the additional add drop for the colorless add drop. So what we had to do, we didn't quite go colorless. That was the ideal that we're going to get to at some point, but not quite yet. What we did was we cheated. Instead of having the 50 gigahertz filters, we changed to having some 75 gigahertz filters instead. It's kind of a hack. It's ugly. It's not the way we're doing it on the rest of the network, but it was quickest and the easiest and the least disruptive to do. But it still means, you know, changing all of these connections to add that. But it wasn't even really quite that easy. So the Sienna boxes, just like your Junipers, just like your Ciscos, has software running on it. And you know what it's like when the bit of software is working, you don't touch it. So we were a couple of releases behind, and there was no direct route up from 10.2 we were running to 12.1, which is what we needed for the 400 gig. So we had to go from 10.2. Update all the nodes now across the network. There are a couple of hundred Sienna boxes, each of which has 2 shelf processors, and you have to kind of load it into one of the shelf processors, swap over, then load the other one, then swap back. And we had to do that then twice, once from 10.2 to 11.2, and once from 11.2 to 12.1. And unlike what you tend to do with the routers, with the WDM kit, the software running on the nodes is very much tied in with the controller software. So this is Sienna's one control software, and there is a direct correlation between the versions of one control and the versions of the network software. So we had to change. We had to coordinate the changes of the management software and of the node software. And we found out, we weren't warned of this, we found out that there was a change in the licensing approach. So instead of everything being on a node, we upgraded the software, and as soon as we did so, license alarms. You are not authorized to have this wavelength, you're not authorized to do this, that, and the other. So we had to deploy a license server. Then we found out that the node software had different power calculations between releases. One of them had a 6 dB margin. They'd tightened that up to a 3 dB margin, which meant that after we did the upgrade, a whole bunch of the wavelengths didn't come into service, instead of waiting for power. And that had to be, we had to go in and manually change the margins on each of those to have them come up. But was it all worth it in the end? Yes, it was. So even the Manchester to Leeds link that was supposed to have been 300 gig, and it actually came up at 400 gig. That card, you can see, the first card with, anyway, the card with the most fibers in is the 400 gig card. So it has the 4 QSFP28 clients, and then at the top is the 400 gig line side card. So where next? So we've just completed upgrading the rest of the network to FlexGrid. Unfortunately, I think we broke our main optical engineer because he's just left us after going through and upgrading every single WSS from the fixed grid to the FlexGrid and rebuilding, in effect, every node. Next up is deploying true colorless add drop. So instead of the hack with the 75 gigahertz add drop, we're going to use what's called the CCMD colorless channel multiplexer, demultiplexer, which will allow us then to do proper FlexGrid add drops. So we can adjust it from having 50 gig to 75 to 100, depending on the size of the wavelength we're going to be using. The problem with that is that some of our original cards now are not certified as working with colorless, so we have to go through and replace those. We'll be deploying 400 gig then over longer spans as well. So instead of the kind of the 300 kilometer limit we were kind of hitting with the WaveLogic AR, you'll be using WaveLogic 5 and doing longer spans. And then there's 400 gig clients. So we've had a bit about what goes in to make a 400 gig transceiver. There's a whole wide variety of options at the moment for 400 gig transceivers. And after that, we're really looking at what do you need? Why do we have to have this WDM layer? Because we have a transceiver in the router, we have another transceiver in the transmission kit, then we have the line server transmission kit. As more and more DSP power is being squeezed into these optics, can we get away with just having mux demux on the optical layer and doing everything in the routers? Now, so far, it's been difficult to do that because the router optics have always been at least a generation behind the dedicated transmission vendor stuff. But maybe there's a way we can, maybe we're getting to the point where they're catching up and the density is there. We're not necessarily relying on CFP1 or CFP2 sized transceivers for 400 gig because the QSFP 56 stuff with a really powerful DSP in it could be a very attractive way of driving coherent, possibly 400 gig from a router. Of course, you then get into power stuff because driving that sort of power from a little thing the size of your finger, dissipating the power for that is awkward. But it's where next? Where do we go from here? Because it's kind of expensive scaling up a transmission layer and a routing layer at the same time. And with that, I think I'm done, and I'm here for questions. Or maybe.
No questions?
Hi, Laura from Felix. When you made the decision to splice in that rack in Manchester, what's that done for your potential repair time? Because these are in racks which are accessed by other people, so obviously clumsy people coming in and wrecking bits of fibre. Is that potentially a problem?
There wasn't really an option. I don't think we haven't actually kind of broken it out and spliced it at each one. We've put in a direct fibre that goes from us to the supplier now, rather than having the intermediary ones. So if that bit of the fibre breaks, then we'll just have to get that a new cable put in, basically.
Right.
And
you weren't going to ask me any questions, Brian.
Brian Nisbet from HEANet. The licensing fun sounds like a nightmare at the end of a bunch of upgrades. Was there any warning, and what was the vendor support like at that point in time?
So Sienna have been really helpful. I mean, even more helpful would have if we'd known it was coming up. But we didn't, and they made sure that we got it sorted out. We were able to deploy a license server within a day and get it up and get the alarms cleared. And what happened? These are licensed alarms. they cluttered up the management display. It didn't stop things working, which was important. So, we might have lost maybe some other alarms that happened in the same time because there is, it was all a massive red, but the services were actually working.
Donald from HENet. Did you have any resistance from Equinix when you said we're going to have to ignore all your infrastructure and run a direct cable to the provider?
No. It was more, again, it's a case of we need this. We've gone through, polished every connector within an inch of its life, and it still wasn't working, and we needed to improve that OSNR to get the signal working. So it wasn't actually a problem. But, yeah.
And any more?
Hi, Tammy Hassan from Zayo. You said as part of the program that you went through re-going over the OTDR results of the fibres. Had you actually seen many changes in that in only a 6-year period?
Not significant changes. There's a few dBs here and there, or a few extra losses from patches and so on. But it was more a case of wanting to be sure that we had some up-to-date results in case there had been changes. We hadn't really seen significant changes, but having the results meant that we were able to do a fairly good simulation with Sienna so that we were fairly confident that it would work or it wouldn't work and needed this splicing work done beforehand. But most of the spans were pretty close to the original OTGR results.
So had you planned for any changes in the optical line system in case you had seen any significant differences?
So that was one of the reasons that we were going from the EDFA-based amps to the Raman amps. So it increases OSNR, but it's also a more powerful amplifier as well. So that was a change in the optical layer to cope with this. But beyond that, not really. I mean, the existing services were still working, so we obviously hadn't gone to heck in a handbasket. And yeah.
Thanks.
Any more questions?
Hello, David from Puppet. One thing I was wondering, you were upgrading quite a lot of nodes over multiple versions of the firmware. How did you go about actually effecting those upgrades?
So, carefully, no. There is an option in the OneControl software to almost do a hands-off upgrade. We don't trust that. It is actually done pretty much node by node. It's a case of loading it onto the backup shelf processor, swapping across SP, loading it onto the main SP, swapping it back. It shouldn't affect traffic. There were times when it needed a cold restart of the shelf rather than a warm restart of the shelf to actually get it working, but it was actually quite a lot of maintenance sessions for our now departed optical engineer.
Thank you.
Behind you.
Hi, Julian. Did you notice any thermal effects of having the increased density of transceivers, either within the data center or within the confines of the Sienna equipment?
We haven't. To be honest, that's a bit of a gap in our monitoring. Most of the time it's a case of if there's no alarms, it's working fine. I might not want to look too closely. Now, these line cards do have maybe a slightly increased power draw than the other ones, but bear in mind what we're switching from. We're switching from 4 or 8 slots of separate 100 gig line and client cards, which each have all their processors onto a single line card. So there's actually a net power reduction in going from the 4x100 to 400. But we haven't got any shelves yet that are loaded up with 14 by 400 gig, so we haven't really measured that.
Last call for questions. Thank you very much, Rob. It was a really good talk. Thank you.